Welcome to the fascinating world of nuclear physics. In this journey we will delve into the heart of atoms, exploring the intricate dance of protons and neutrons. These particles, the building blocks of atomic nuclei, possess a fundamental property called angular momentum. Imagine it as a spin, like a tiny ballerina pirouetting on the stage. This essay will unravel the mysteries of angular momentum, focusing on two light nuclei tritium and helium-3. We will discover how these nuclei form, how their spins combine, and what makes them unique. Get ready for an adventure into the quantum realm. Our journey will take us through the concept of spin, a fundamental property of particles. We will learn how the spins of protons and neutrons combine to give a nucleus its total angular momentum. This exploration will reveal the fascinating rules that govern the behavior of these tiny particles. Imagine a proton or a neutron as a tiny sphere spinning like a top. This spin is called intrinsic angular momentum, a fundamental property of these particles just like their mass or charge. We measure this spin in units of the reduced Planck constant, often denoted as h, pronounced h-bar. Protons and neutrons belong to a family of particles called fermions. Fermions have a peculiar characteristic. Their intrinsic angular momentum can only take on half-integer values, specifically plus h/2 or minus h/2. These two possible spin states are often referred to as spin up and spin down, respectively. Now let's bring these spinning particles together to build a nucleus. The total angular momentum of a nucleus is the sum of the intrinsic angular momenta of its protons and neutrons, plus any additional angular momentum due to their motion within the nucleus. This combined angular momentum plays a crucial role in determining the properties of a nucleus. Let's start with a simple nucleus deuterium, also known as heavy hydrogen. Deuterium consists of one proton and one neutron bound together. Remember, each of these nucleons has an intrinsic spin of plus h/2 or minus h/2. In deuterium, the proton and neutron can align their spins in the same direction, both up or both down, or in opposite directions, one up and one down. When their spins are aligned, we get a total spin of plus h, 1/2 plus 1/2 equals 1. When their spins are opposite, the total spin is 0, 1/2 minus 1/2 equals 0. The total angular momentum of deuterium's ground state, its lowest energy state, is 1. This means that the proton and neutron spins are aligned, contributing a total spin of 1. The orbital angular momentum of the nucleons in the ground state is 0, so the total angular momentum equals the total spin. Now, let's add another nucleon to our deuterium nucleus. If we add a neutron, we get tritium, a radioactive isotope of hydrogen. If we add a proton, we get helium-3, a stable isotope of helium. When we add a nucleon, we need to consider its spin and how it couples with the existing spin of the deuterium nucleus. The new nucleon can either align its spin with the total spin of deuterium, or anti-align it. For example, if we add a neutron with spin up plus h/2 to deuterium in its ground state, total spin 1, the total spin can become either 3/2, 1 plus 1/2 equals 3/2, or 1/2, 1 minus 1/2 equals 1/2. The actual total angular momentum of the resulting tritium nucleus will depend on the specific quantum state. Section 5. The Pauli exclusion principle, a rule for nuclear roommates. Not all possible combinations of angular momentum are allowed in a nucleus. The Pauli exclusion principle, a fundamental rule in quantum mechanics, dictates that no two identical fermions, like protons or neutrons, can occupy the same quantum state within a system. In the context of a nucleus, this means that no two protons or two neutrons can have the same set of quantum numbers, which describe their energy, angular momentum, and other properties. This principle limits the possible spin configurations for tritium and helium-3. For example, in helium-3, both protons cannot have spin up, or plus h/2 in the ground state. One of the protons must have spin down or minus h/2 to satisfy the Pauli exclusion principle. This constraint plays a significant role in determining the allowed angular momentum states of nuclei. Section 6. Unraveling helium-4, removing a nucleon. Let's turn our attention to helium-4, a very stable nucleus consisting of two protons and two neutrons. Its total angular momentum in the ground state is 0. What happens if we remove a nucleon from helium-4? Removing a neutron from helium-4 would leave us with helium-3, We already explored the possible spin configurations for helium-3 earlier. The actual angular momentum state of the resulting helium-3 nucleus would depend on the specific quantum state involved in the removal process. Similarly, removing a proton from helium-4 would result in tritium. Again, the specific angular momentum state of the tritium nucleus would depend on the details of the removal process. Section 7, Lithium-5 and Helium-5 Unstable Isotopes. Moving beyond tritium and helium-3, let's consider two more exotic isotopes, lithium-5 and helium-5. These isotopes are highly unstable and decay very quickly. Both lithium-5 and helium-5 have a total angular momentum of 3/2 in their ground state. This arises from the specific arrangement of protons and neutrons and their spins. The instability of lithium-5 and helium-5 is related to the fact that their extra nucleon, a proton in lithium-5 and a neutron in helium-5, is only weakly bound to the core nucleus. This weak binding makes them prone to decay into more stable configurations. Section 8, Spin Parity, a fundamental property of nuclei. In addition to spin, another crucial property of a nucleus is its parity, denoted by either plus, even, or minus, odd. Parity describes the behavior of a nucleus's wave function when its spatial coordinates are inverted. A nucleus with even parity remains the same upon spatial inversion, while a nucleus with odd parity changes sign. The parity of a nucleus combined with its total angular momentum determines its overall behavior in nuclear reactions and interactions. For example, the ground state of lithium-5 has a spin parity of 3/2 minus, meaning its total angular momentum is 3/2 and its parity is odd. This spin parity combination influences how lithium-5 interacts with other particles and governs its decay modes. Section 9. Conclusion. The significance of angular momentum in nuclear physics. Our exploration of angular momentum in tritium, helium-3 and beyond has revealed the intricate dance of protons and neutrons within atomic nuclei. We have seen how their spins combine, constrained by the Pauli exclusion principle, to give rise to a nucleus's total angular momentum. Understanding angular momentum is crucial in nuclear physics. It dictates the allowed energy levels of nuclei, influences their stability, and governs their interactions with other particles. From the radioactive decay of tritium to the fleeting existence of lithium-5, angular momentum plays a central role in the drama of the atomic nucleus. The study of angular momentum in nuclear physics continues to unravel the secrets of matter's smallest constituents, leading to a deeper understanding of the universe's fundamental building blocks and the forces that govern them.